welcome back to the Central Ray Podcast, your go-to place for clear, confident and practical exam prep for radiography students and working technologists alike. So whether you're gearing up to sit the ARRT radiography registry or just brushing up on your knowledge for CQR, you are exactly in the right place. And speaking of being in the right place, apologies if the audio sounds a little different this week, as I am currently on the road in Orlando, Florida at a dance convention where my son is competing. Hopefully the next episode, or possibly the one after that, should be back in my studio. So today we are diving into a cornerstone of our profession, and that is principles of radiation physics. Specifically, we will walk through items 1 through 4 of this section as outlined in the ARRT content specifications, and those are 1. X-ray production, 2. Target interactions, 3. X-ray beam characteristics, and 4. Photon interactions with matter. So there's a lot to cover, so settle in, feel free to pause and take notes as we go, and don't worry if some of this seems a little abstract at first. We will tie it back to clinical examples and questions you might see on the exam. Sound good? So let's jump in. Part 1. X-ray production. First up is X-ray production, which really begins inside the X-ray tube. We often take it for granted, but it is worth knowing this process inside and out. So what are the steps? Well, X-ray production relies on 4 key things, and that is a source of free electrons, the acceleration of those electrons, being able to focus them into a tight beam, and then decelerating them at the target to produce the X-rays. Let's unpack each one. We get our free electrons through a process called thermionic emission. When we apply current to a filament in the cathode, it heats up and boils off electrons. You can think of this like steam rising from boiling water. The heat liberates the electrons from the filament surface. Next, these electrons are accelerated across the vacuum tube by applying a high voltage between the cathode and the anode. This voltage is controlled by the kVp that you set on the control panel. The higher the kVp, the faster those electrons move, and the higher the energy the resulting X-rays have. But before they hit the anode, they are kept tightly focused into a beam by something called the focusing cup. This negatively charged cup helps prevent the electron cloud from spreading out, ensuring the beam hits a small, specific area on the anode. Finally, when those fast-moving electrons slam into the anode target, they decelerate rapidly. That sudden loss of kinetic energy is what produces the X-rays and a lot of heat. In fact, about 99% of the energy is converted into heat, and only about 1% becomes useful X-rays. So, quick check-in. Can you visualize these steps in your mind? The cathode heats up, the electrons accelerate, they are focused, and then they decelerate at the target to produce the X-rays. That is the foundation of every image that we take. Part 2. Target interactions. So now let's talk about what happens when electrons hit the anode target. This is all about target interactions, and there are 2 primary types that you need to know: Bremsstrahlung radiation and characteristic radiation. So Bremsstrahlung, or braking radiation, occurs when an incoming electron passes close to the nucleus of, in this case, a tungsten atom for a routine diagnostic X-ray. The nucleus's positive charge causes the electron to change direction and slow down, losing energy in the form of an X-ray photon. The closer the electron passes to the nucleus, the greater the deflection and the higher the photon energy. Characteristic radiation is a little different. It happens when an incoming electron knocks an inner shell electron, usually from the K shell, out of its orbit. This leaves a vacancy, and an electron from an outer shell falls down to fill it. The energy difference between those shells is released as a characteristic X-ray. So why does this matter? Because Bremsstrahlung produces the majority of the X-ray beam at diagnostic energies, while characteristic radiation becomes significant at kVp levels above 70. And this is because of the binding energy of the K shell of the tungsten atom. On boards and in practice, remember that most of our X-ray photons come from Bremsstrahlung interactions. So here's a quick quiz question for you. At 60 kVp, do you expect more characteristic or more Bremsstrahlung photons? If you said Bremsstrahlung, that would be correct, since characteristic X-rays in tungsten don't occur until about 70 kVp. Part 3, X-ray beam characteristics. Moving on to the X-ray beam itself, let's discuss its characteristics. When we talk about the X-ray beam, we are describing a few key properties: the frequency and wavelength, the quality and the quantity, primary versus remnant radiation, the inverse square law, and some fundamental behaviors. Frequency and wavelength are inversely related. Higher energy X-rays have higher frequency and shorter wavelength. This is what gives them penetrating power. When we say beam quality, we mean the energy of the beam in terms of its penetrating ability, which is primarily controlled by kVp. Higher kVp equals higher beam quality. Beam quantity refers to the number of photons in the beam, which is primarily controlled by MAS. More MAS equals more photons. What about primary versus remnant radiation? Primary radiation is the beam that exits the tube and heads towards the patient. Remnant or exit radiation is what comes out of the patient and exposes the image receptor. That's the useful signal we actually create the images from. And of course, don't forget the inverse square law. The intensity of the beam is inversely proportional to the square of the distance from the source. So if you double your distance, the intensity drops to 1/4. This is vital for both patient and technologist protection and shows up plenty on our exams. Lastly, remember the fundamental properties of X-rays. They travel in straight lines, they can ionize matter, and they have no mass or charge. They are highly penetrating and invisible, but they can damage tissue, which is why our next topic is so important. Part 4, Photon interactions with matter. Finally, let's wrap up this episode with photon interactions with matter, the physics of how X-rays interact with the patient's tissues. There are 4 main interactions that you need to know: photoelectric effect, Compton scattering, coherent or classical scattering, and then the attenuation principles. The photoelectric effect happens when a photon completely transfers its energy to an inner shell electron and ejects it from the atom. This interaction produces contrast on the image because it occurs more readily in tissues with higher atomic numbers, such as bone. Compton scattering, on the other hand, is when a photon transfers part of its energy to an outer shell electron and is deflected. This scattered photon can degrade image quality and expose personnel, so we use grids and shielding to minimize its effects. Coherent scattering is less common and occurs when a low-energy photon interacts with an atom and changes direction without losing energy. This has minimal impact at diagnostic energies, but does contribute slightly to a fog. Lastly, we need to consider attenuation, which refers to the reduction in the beam intensity as it passes through matter. The thicker the tissue or the higher its atomic number, the more attenuation occurs. That is why soft tissue appears darker on an image, while bone appears lighter. Bone attenuates more of the beam. And there we have it, the 4 major concepts at the heart of radiation physics: how X-rays are produced, the target interactions that generate Bremsstrahlung and characteristic radiation, the key characteristics of the X-ray beam and how we describe them, and the ways photons interact with matter to create contrast and scatter. So take a moment to reflect on these before you move on. Being comfortable with these concepts will not only help you pass your exam, but make you a safer and more effective technologist. So here are a few questions to think about. Number 1, At what kVp level does characteristic radiation become significant in tungsten targets? 2. Which beam characteristic is controlled by kVp, the quality or the quantity? And 3. What interaction is primarily responsible for image contrast in bone versus soft tissue? So please leave a comment or respond in the comments if you think you know these answers. So thank you for tuning in today. In our next episode, we will keep going in the safety section. So be sure to subscribe and join me next time as we tackle the next steps in radiation physics and radiobiology. And if you are watching this on YouTube, remember to hit that little bell button so that you get notified the next time I release an episode. So until then, keep studying and keep practicing and keep being the difference in your patients' lives. See you next time.